High above Los Angeles, on a silent mountain peak, scientists have been watching the sun for more than a century. Not for minutes, not for headlines, but for patterns that unfold over decades. And among those who studied this historic record was Dr. Willie Soon, a solar researcher who believed the key to understanding long-term solar behavior was hidden in these archives. But here's the real question. What happens when a scientist builds arguments on 100 years of solar observations, and the scientific world doesn't fully agree on what those patterns mean? Stay with me, because this story is not about a telescope. It's about data, persistence, and a debate that begins with the sun itself. Dr. Willie Soon did not begin his career as a climate commentator or public figure. He trained as an aerospace engineer at the University of Southern California, earning his PhD in 1991. His early work focused on high-temperature gas kinetics, complex physics tied to extreme environments. But his career shifted toward astrophysics and solar research. In 1992, he became associated with Mount Wilson Observatory, one of the most historic astronomical sites in the world. This observatory is famous for helping Edwin Hubble prove that the universe is expanding, but it also quietly built something else. One of the longest continuous records of solar activity ever collected. And for Dr. Soon, that record mattered, because he was not chasing solar flares or dramatic explosions. He was interested in long-term solar variability, slow changes in the sun's behavior that only become visible over generations. What could a century of sunspot data reveal? And how much weight should that data carry in modern scientific discussions? Mount Wilson Observatory began systematic solar observations in the early 20th century. Day after day, astronomers recorded sunspots, dark regions on the sun caused by magnetic activity. These sunspots follow an approximately 11-year cycle. Activity rises, then falls, then rises again. But beyond that rhythm, researchers noticed longer-term patterns, extended highs and lows that stretch across decades. One famous example is the Maunder minimum, a period between 1645 and 1715 when sunspots nearly disappeared. Dr. Soon co-authored work examining historical solar records, including research related to long-term solar variability and the Maunder minimum period. At Mount Wilson, he had access to carefully preserved solar archives, photographic plates, magnetic field measurements, and long-run datasets. And here is where the tension begins. Because long-term data can be interpreted in different ways. Does it show subtle solar influence over extended periods? Or are those variations too small to drive major change? How do you measure something that unfolds across centuries? Scientific disagreement does not begin with headlines. It begins with interpretation. Dr. Soon's research emphasized the importance of natural solar variability in understanding long-term patterns. He argued that extended solar cycles and magnetic variations deserve serious attention in scientific modeling. Some researchers agreed that long-term solar data is valuable, but questioned how large the solar impact might be. Others argued that modern measurements show limited variation in total solar irradiance compared to other forces. This is where Mount Wilson's historical record becomes central. Because older data must be calibrated carefully. Instruments change. Techniques evolve. Observers differ. Small measurement differences can compound over decades. Supporters argue that long-run datasets provide critical context. Critics argue that reconstruction uncertainties make interpretation complex. So the debate is not about whether the sun changes. It does. The debate is about magnitude and influence.